Hey guys, welcome to Deep Codes, and in today's video we will discuss LeetCode question 1569 that says number of ways to reorder array to get same binary search tree. So guys, this is very good question in order to revise recursion as well as binary search tree as well as permutation combination mathematical concepts in by doing one single problem. So guys, stick till the end and watch the complete video. Now here you would be given one array, and from that array you will form one binary search tree. Okay, so from the input array you will form binary search tree. Now you need to apply some permutation to the input array such that the permutation would also result into same binary search tree, and at the end you need to return how many such permutation of the array is possible. Okay, so for an example, let's say you are given this array nums 213. So the binary search tree possible from this num set is the root 2, then the left node has a 1 and the right node has a 3. So this binary search tree is possible from the given input. Okay, now you need to find permutation of this given input such that the permutation also result into same binary search tree as this. So one such permutation is, let's say, 231. Okay, this is one permutation of this given num set. Now if you try to form binary search tree of this, so 2 would be the first node, it would be the root. Now 3 is greater than 2, so it would be at the right child or the right subtree, and 1 is lesser than 2, so it will be a part of left subtree. So this is one permutation of the given input whose binary search tree is the same as this. Okay, now let's say if you form a different permutation like 3 2 1. So here if you try to form binary search tree, it would be something like this: 3 as a root, 2 is lesser than 3, so it would be a part of left subtree. Now 1 is also less than 2, so it would be part of your left subtree. So this binary search tree is somewhat different from the input, right? This is different, so we can't consider this as a valid permutation. So the only valid permutation for the given input 213 is 231. This is only valid permutation, so yeah, we have to return the count of such valid permutations. Okay, so count is 1 here. So I hope you guys have now somewhat understanding of what this question asks us to do. The question tells us that we need to find valid permutation of the given nums array, and this word valid states that the binary search tree of the permuted array must be the same as the input array. Okay, so yeah, we need to apply some logic and we need to find the count of such valid permutations. So now let's try to move on and let's take a look at the second example. So here in the input array you are given 2 3 5 1 2 4 5 1 2. Okay, and from this 2 4 5 1 2 you can form sub binary search tree like this. So 3 as the root node, 3 would come here. Now 4 is greater than 3, so it would come here. Now then 5 is greater than 4 and also greater than 3, so it would come here. The next is 1 is lesser than 3, so so towards the left subtree. 2 is less than 3, so it would be a part of left subtree, but 2 is greater than 1, so it would be here towards the right of 1. So guys, this is the binary search tree for the given input 3 4 5 1 2. Okay, now we need to find valid permutation. So in the explanation part we are given a few of the valid permutation. So let's try to draw binary search tree for the first one. So it's, let's say, so it is 3, so 3 is the root. Now 1 would be the part of left subtree, so 1 would come here. 2 is lesser than 3 but greater than 1, so it would be here. Then 4 is greater than 3, so here. 5 is greater than 3, so right subtree. 5 is also greater than 4, so towards the right. Now if you compare both this binary search tree, both are same, so yeah, that's why this is one valid permutation. Similarly, you can try to draw binary search tree of this different permutation, right? This 5 different permutation, and all would result the same like this binary search tree. Okay, so just for an example, let me try to draw for this fourth one. So 3 as a root, 4 is greater than 3, so it would come here. Then 1 is less than 3, 2 is less than 3 but greater than 1, 5 is greater than 3, also greater than 4. Yeah, this is the same. So guys, all these 5 permutation given here in the explanation are the valid permutation, and if you try to draw binary search tree, then that would result the same as binary search tree for the given num set. Okay, now guys, if you try to draw different binary search trees for this given input, you can observe one thing. And what is that key observation? Let's try to figure out. See, the first element of the nums array or any of the combination would be same because they would be the root node. Okay, the first element of the nums array as well as the resulting permutation must be same because the root node must be same. In order to make binary search tree similar to binary search tree similar, the root must be same, all the left child must be same and all the right child must be same, but starting would be comparing with from the root, so root must be same. So let's say for any given input of nums, let's say you are given nums input like n1, n2, n3, n4 and so on, this n1 would represent root. Okay, it would represent root, and all valid permutation would also have one thing common: the first index element, that is n1, would remain the same. This would vary afterwards, the elements can vary, but this would remain the same because our root must not change in order to make similar binary search tree. Okay, this is the first thing. Now guys, since this is a binary search tree, we can utilize the property of binary search tree. So the property of binary search tree says that all the elements in the left subtree are lesser than the root. So if it is 3 and all the elements on the left subtree are less than root, and all the elements on the right subtree are greater than the root. Okay, so this observation will help us to come up with a solution. Okay, so guys, clear till here? So the observation what we made here till now is, so for any nums array, the first element or the 0th index element is fixed because it is a root element. So for any of the permutation of the nums array, the 0th index element is fixed. Now the there would be two parts: the elements in the left subtree and the right subtree. So all the elements lesser than the root would be part of left subtree. So here 1 and 2, and 4 and 5 would be the part of right subtree. Okay, clear till here? Now guys, one more thing we need to observe here is the relative position is fixed. So for this 1 and 2, the relative position is fixed. 4 and 5 relative position is fixed. Now you might be having a question that what this means, what is the relative position? Okay, let's try to figure out. So if you, for the given nums array, this nums array 3 4 5 1 2, so if we make one permutation like this 3 1 2 5 4, so here we change the relative position. So this relative position means that if you have something like this 1 and 2, then 1 and 2, that means 2 must come after 1 inside the permutation, and 4 and 5, that means 5 must come after 4 inside the permutation. What if this condition is not satisfied? So let's say here in this example we have taken 3 1 2 5 4. So instead of 4 5, that means 5 must come after 4. We have changed this and violated this condition, this relative position fixed condition. We have changed the relative position, that means 5 4. Now how does that impacts? Okay, so let's try to draw a binary search tree. So initially comes the root, 1 is less than 3, so in the left subtree. 2 is less than 3 but greater than 1, so here. Then comes the 5 is greater than 3, so comes here. And 4 comes here, that is greater than 3 but less than 5. Now if you observe this binary search tree, this is different from the input. Okay, this is different from the input binary search tree. That is because we have changed the relative position of the left subtree and the right subtree. We have changed the relative position of the nodes inside the left and right subtree. And if we do that, then the resulting binary search tree is not a valid binary search tree. So we have to keep this in mind, that the relative position must not be changed. Okay, if you observe here all this given valid permutation, the relative position is fixed. That means 2 must come after 1. So let me show you. 2 must come after 1, 5 must come after 4. So that is 4 comma 5 2 comma, the relative position is fixed. So in all the valid permutation, say 2 comes after 1, 5 comes after 4. So guys, 3 observation. First is the root is at the index 0 and that is fixed element. Second is all the elements lesser than the root are the part of left subtree and greater than the root are part of right subtree. Okay, so from that we came to know what are the elements of the left subtree and what are the elements of right subtree. Now all the elements of the right subtree have the fixed position relatively, means inside the left subtree they cannot permute, and inside the right subtree the nodes cannot permute or cannot change the position. So relatively the position is fixed. Okay, but we can change like this: 1 4 5 2, 1 4 2 5, but 2 must come after 1 and 5 must come after 4. So I hope you guys have now understood that what I'm trying to tell. Okay, So things are clear till here, right? Now we need to think that how we can calculate the valid number of permutation. We know what is valid permutation, what condition must be satisfied for a given permutation to be valid. We know that, okay? But now we have to find some way to count number of valid permutation, okay? So for, let's say, for this given norms array 3, 4, 5 and 2, we are taking the same example here. 3 is the root, we know, and left, oh sorry, this is not the left but the right. These are the part of right subtree, and the right subtree will have elements 4 and 5 with their relative position fixed, okay? Now we need to find the what are the different places where we can keep 4 and 5, okay? So if you take a look here, that this is the given norms array, this is the norms array of a size 5, like with the index 0, 1, 2, 3 and 4, and the first element is always fixed, okay? This is always fixed because it is a root. So, but this 4 and 5 can change the position. They can either be here or here or here. So there are 6 different combinations of this 4 and 5, right? 4 and 5 can be fixed. So if we count anyone, like if we count the number of ways to arrange this 4 and 5 such that 5 must come after 4, then we will get the answer. So here there are how many different position are there for 4 and 5? Keeping 3 as fixed, there are 6 position, and from that we would subtract 1 by 1 because 1 is itself the valid, that is valid input is also valid, so we will get 5 answer here. So if you take a look, we are getting 5, and with the given nums array total are 6, okay? But in the answer we have to return number of valid permutation minus 1 because 1 is for the answer itself. So guys, these are the different valid position for 4 and 5 where we can keep, okay? Basically there are only 4 blocks that can be used because first is fixed, and inside the 4 blocks we can keep this 4 and 5 in 6 different ways, okay? So once we know that how we can select the places for any one of the subtree, either the left subtree or the right subtree, then the answer is solved. Then the question is solved. We will get the answer because the remaining boxes will be occupied by the other subtree. Let's say we have arranged the right subtree, then the remaining would be occupied by 1 and 2, that is the part of left subtree 1 and 2, and also the relative position of 1 and 2 would remain fixed, right? That we have already discussed. So guys, our question reduces to find the number of position or places where we can keep any one of the subtree, right? Where we can keep the nodes of any one of the subtree. Like here we have kept 4 and 5. And if you have somewhat idea of permutation combination mathematical concept, then you can solve this easily, okay? So finding this mathematically can be done by this formula, that is n-1 combination of number of nl. Nl is nothing but number of nodes in the left subtree, left or right subtree, whatever you can take. And by n-1 because the first position is fixed. So if the array or the nums array is of a size 5, the first position is always fixed for the root. So the remaining is n-1, and from that n-1 we need to find or choose the position for nl elements, or means number of elements in the left subtree. So let's say the number of elements in the left subtree is 2 and n-1 is 4. Now if you apply this combination formula, then it would be something like this: 4 factorial upon 2 factorial multiplied by 4 minus 2 factorial. So that would result in 24 divided by 4, and that is 6. Okay, and you can see here that these are the 6 different combinations where you can keep 4 and 5, right? These 6 are 6 different places where you can keep 4 and 5. So we can derive this mathematically by using this formula. Okay, clear till here? So now, but another thing here is, so this I already told you, this total combination is 6, but we have to subtract 1 and to get the answer, because 1 is the position of the input array itself, that is the valid permutation. Now let's say you have some large input like this. Okay, this is a big binary search tree. So here we have 12, the 4 is less than 12, so here 11 is greater than 12, so here. Now the next element is 2 is less than 12 as well as less than 4, so it would come here. So if you try to make binary search tree for this given input, it would result in something like this. Okay, now here what we have did is we will find what are the elements in the left subtree. So this would be a part of left subtree, and this would be the part of right subtree. Then we can apply this combination formula and get the answer. But we are not done yet, because if you observe this left subtree, this left subtree itself has left and right subtree, right? And this, from this whole subtree, the nodes can also be arranged, right? So guys, that's why we have to also do this recursively. See, this was a complete tree. Taking a root as a 12, this was a complete tree where this was the left subtree and this was the right subtree. Now, inside this left subtree, taking root node as a 4. 4 also has its separate left subtree and separate right subtree, whose elements can be arranged, right? So we have to apply this combination formula recursively, right? We have to apply recursively for all the left and right subtrees. Okay, got it? Clear till here? So we need to solve recursively for each subtree, right? So I hope you guys have understood that first we take the big left subtree, then the right subtree, then we take the inner left subtree and inner right subtree, right? And we solve this question recursively. Okay, so that's why we will use recursion here. Now we also know how we will do permutation, how we will find the count of the valid permutations, right? Now one more thing we have to do here is we need to find or calculate that combination formula and how we can do that efficiently. So if you try to do combination applying the formula by taking factorial each time, then that would result in more time, right? If you try to go to find factorial of each number every time and then make a division, then that will take more time. But we can reduce that factorial time and the time taken to derive the answer of this combination formula by using one famous triangle, that is Pascal triangle. Okay, let's take a look how Pascal triangle help us to compute this result. So let's say you have a Pascal triangle of a size 4 cross 4. So here you have elements from 0, this is 5 cross 5. So from 0, 1, 2, 3, 4, and here also you have elements 0, 1, 2, 3, 4, and you have 1 here. Okay, all these fields are all these edges, or you can say the first and last, are always filled with 1. Okay, the Pascal triangle. Now how this 2 is filled, how these middle elements are filled, they are filled nothing but sum of above 2. So this will fill by sum of this and this would be filled by sum of this and this. So if you take a look here, how 3 we got 3 is nothing but sum of 1 and 2. This 3 is nothing but sum of this 2 plus 1. 6 is nothing but a sum of this 3 and this 3. So table of ij is nothing but a summation of I minus 1j and I minus 1 j minus 1. So 6, how we get 6? That is I minus 1 j minus 1 plus I minus 1 j. So these two element summation we will get 6. These two elements 6, 3 plus 1 would result in 4. So this is how we derive this Pascal triangle. Now how this Pascal triangle would help us? So guys, if you want to find the answer of 2c3, okay, then that would be this. That is the second column and the third row. If you want to find 4c2, that would be nothing but this 6. This is the fourth row and the second column. So you will get answer like this. Okay, sorry guys, this is wrong here. I guess it would be 3c2. The above number must be greater than this one. So yeah, it would be 3c2 here. So whatever, if you want to find 4c2, then you take a look at the fourth row and second column, right? And that's where you will get the answer. So this is how you will apply the combination formula. Now guys, combining all this, that is how to find permutation formula, how we will solve this recursively, and combining all these things, we will move on to the coding. Now here let me explain you the code we took a mode and this table. This table is a Pascal triangle or a Pascal table. Now here, this is our DFS call, or this is our recursive call. But first let's take a look of how we calculated this Pascal triangle. So we took a table of size n plus 1, and yeah, each row would be I plus 1, right? And we take table of I as summation of I minus 1 j minus 1, that is the previous element, and this is top element, right? I minus 1 j. So summing this, we'll get this answer, and then we call this recursive function DFS. Now in DFS, this is our base condition. So n less than equal to 2, that means the size of the nums array is less than or equal to 2. Okay, that means there would be only 2 elements, and when you have only 2 elements, there would be only one possible combination of a binary search tree. So this would be our base condition, where only less than or equal to 2 elements are there in the nums array. We would directly return 1. Okay, got it? Because there is only one combination of a binary search tree. Now we will find how many elements are there in the left subtree and the right subtree. So all the elements whose values are less than nums of 0 or the root would be the part of left, and the remaining elements would be the part of right. Now what we will do is, as I told you earlier, that we will call this function recursively for the left subtree and the right subtree, and that's what we are doing here. We are finding the answer from the left subtree, so calling the function with left, finding the answer from the right, so calling the function with the right subtree. And then here we are calculating the actual combination formula. Our formula was what? It was n-1 c number of elements in the left subtree. So n-1, we took table of n-1, that is the row index, and the column index is L length, so length of the left subtree. Okay, multiplied by the answer that we got from the left subtree and the right subtree. See guys, we have to multiply, not addition, multiplication, because because we need to find the different permutations. So inside the permutation, let's say here you get answer 3, and here from the left you get answer 2, and here 1. So that means it is not 3 plus 2 plus 1, it is 3 multiplied by 2, right? It is, you won't do addition here, you will have to do multiplication. That's how permutation and combination works. Okay, and at the end we do the mod and return the answer. So the answer, we will get answer here, and we do mod and also subtract 1, because the given input term value is also valid, and we have to subtract that valid input. So yeah guys, doing all these things recursively as well as using this Pascal triangle, we will get the correct answer. So I hope you guys have now understood that what we are doing here and how we are doing that. Now talking about the time and space complexity, the time complexity of this approach is big O of n squared. Why n squared? Because this Pascal triangle creation would take big O of n square time. Okay, because see, this table is itself big O of n square, because for each index we are appending one another vector, right? For each table of 5 we are adding one another vector, and computing this will take big O of n square in worst case. Also the recursion will also take big O of n square, because we are not doing recursion for one nums array. We are splitting the nums array into left and right, and again doing the recursion. See, this is again doing the recursion on this left complete subarray and right complete subarray. So this will also take big O of n square time complexity in the worst case. Okay, yeah, and the space complexity is also big O of n square. As you can see, the Pascal triangle, this would be nothing but a 2D vector. So yeah guys, that's all for this video. If you guys have any doubts, then do let me know in the comment section. Make sure you like this video and subscribe to our channel. Thank you.